Okay. Okay, let's get started. Again. Okay, I have here a little short video clip of water waves traveling through two openings where we have waves coming in, striking it. The waves spread out in circular fashion from the individual things. Let me freeze this thing for a second here. Drive us crazy. The idea that these waves are, we say, interfering. Here you can kind of see classically that where you see like the crest of one wave, it meets the trough of another, and between these two is what we call a nodal line, where these are minima, and there's nothing really there. In fact, in terms of watching the water, you'll notice that it's perfectly still in these nodal regions. I'm going to idealize that a little more with this ideal here, where we're going to deal with just a couple point sources that are radiating off in a circular fashion, and they're interfering. They have this idea that at those regions there's cancellation in terms of light instead of water. This represents just blackness. There's no light there. And that where there's waves, these are maxima. The idea that, again, that light, we can project this along the central line. We call this the central maximum. We have this pattern repeating of light and dark. We're going to name these things, the central maximum. And then we're going to talk about other maximas as M1, M2, M3. We can go off in the other direction, -1, -2, -3. And we need to get developing some basic ideas. Now, if we take kind of a cross-section of these two waves, they're emanating from these two slits. We say that the waves, as they're coming in here, are in phase. They were struck by light. They're happening in phase. When they get out to here, since they travel exactly the same distance, they're still in phase. And we can look at these waves as having constructive interference. Crest is crest is added with crest, and trough with trough. If we start to move off from that a little bit to this first, we say first minimum, we actually have a few extra waves in here. In fact, we have an extra half a wave in there, and that throws these two out of phase with one another, and they have destructive interference. This pattern repeats and repeats as we move across the screen, and hopefully you're pretty comfortable with that. Now, as far as doing calculations, we're going to look at this region down here to tell the story. Right now we're at the central maximum. There's the same number of waves in both the top slit as the bottom slit. And as we start to move off, we move off at a little bit of a difference. There's a little extra distance here. And the idea that if we go in that little extra distance, which is under the magnifying glass, is just a half a wave, that's going to give us destructive interference. So there's 1/2 wavelength. There, giving us our first destructive. As we move off to the maximum, we have the first one, m equal to 1, we have one complete wave in there. And that throws them back into phase. If they started out in phase and they're in phase here, they then travel the same distance out to the screen, they're still going to be in phase. We can repeat this. And again, the idea, the most important idea, is this distance here is what's going to tell us what's going to be happening. We can look in general with this idea that the screen we're assuming is a great distance. So these are virtually 90 degrees. The angle out to the screen is what we'll call theta. And I think I got one here with these things labeled here. There's some distance out to the screen, L. Theta represents the position up on the screen as measured here. The idea that there should be similar triangles here, that this path difference, this is what's going to be key, where we're going to fit in extra waves, this path difference should be equal to some whole number of waves when we get out to the screen. So the idea that we'd say d sine theta, that path difference, if that's equal to a whole number of waves where m can take on the value of either 0, 1, 2, 3, and so on, this would give us what we call our maxima. Maxima, this would be our bright fringes. If we have an additional half wave in there, so it's like 2.5 or 3.5, d sine theta, that path difference, is equal to m plus an additional half of waves. This would be a dark fringe or a minima. Okay, and now when we're doing this, this is our basic equation. Sometimes we can make small angle approximations. L is the distance out to the screen. And if you need to find theta, what you really should do is say that the tangent of theta is equal to y over L. And sometimes when we're dealing with small angles, which we usually are for most double slit things, where we're small, we can say that the sine, this is for small angles, we can say that the sine of theta is approximately equal to the tangent of theta, which is equal to y over L. So very often in problems, and we get doing this so automatically that we say that d sine theta, or instead of d sine theta, equal to m lambda. Or we'll just write this as dy over L is equal to m lambda. And so this is just kind of a convenient shortcut. And this would be a maxima. And then a minima would be dy over L time is equal to m plus a half a wavelength. Okay? So these are handy. They're used a lot in homework problems. They can be deceptive in the sense that sometimes the angles aren't small. And something that he covered in chapter 38 could really be discussed right now is the idea of a diffraction grating. Diffraction grating is a bunch of slits. And the idea with that is that if we have a number of slits, like the pattern out on the screen, for 2 slits, has our familiar pattern. As we start to add slits, we get a similar pattern for the maxima. If we've got 3 slits, 2 slits could be interfering and giving you a minima, and that third slit might give you just a little bit. So in that case, it gives a little what we call secondary maxima here. But the position of this, where the central maxima would be as if all 3 slits all lined up in phase would give us the bright fringes. And those are going to be in the same position as they would be for 2 slits. If we go to 4 slits, we get, again, secondary maxima here. Here's 5 slits. We get n numbers of slits. These start to wash out. And what happens is we get a finer, more sharply defined maxima where we're located. This is very good for when we're dealing with diffraction gratings. If we have a diffraction grating, we have a great number of these things. For instance, the ones, just the little toys we were playing with, I use these in demos. These have got 500 lines per millimeter. The equation you'll use for these things is going to be the same as you would for 2 slits. You need to get the d, the distance between any 2 adjacent slits. So if you take 1 millimeter divided by 500, that would tell you what d is. Typically, these distances get to be very, very tiny, and we can get some very large angles with these diffraction gratings where the angles can be very large, even out to 90 degrees. Can't go beyond 90 degrees. You have a homework problem on that. But the idea of all the stuff that's developed here applies to diffraction gratings as well. But don't, if you have a diffraction grating problem, first go in to do this, get your angle, then go back and figure out what the sign is. Don't automatically assume that it's a small angle. If in doubt, do it right. Okay, looking at that, let's see. Okay, let's, in fact, I think this might be good just to deal with some problems. How about number 3 on the practice problems? Okay, now here it's got 2 colors of light. Now, some people get confused by this. They say, oh, wait a minute, 2 colors? Well, how can this be? How can you have 2 colors? The idea that you have your you have your slits. Maybe I'll just kind of do a quick sketch here. This represents your 2 slits. There's some distance d apart. They're going to be out on the screen. There's going to be, the screen is positioned, let's say, some length L away. Now you can shine light through this. This could be any kind of light. You could even shine 2 lights through this, and at the same time. They just go right on through. You've got one light, which is, a first color is some wavelength. We need to find out what these wavelengths are. He says it's positioned the screen 1.5 meters away. And this first one will form a bright spot out here, would be a maximum. Let's call that position lambda 1. Now, if it's bright there, we would say that it's got some wavelength, so that there's going to be some angle out to the screen, and we can use this small angle approximation that it's got some y. Let's call it y1. And he says that this y1 is 1.88 centimeters from the central maximum, so it's up here this distance. He's got another color that is he says second color is 0.37 centimeters from that. Now I interpreted it in my solutions that it's 3 centimeters this direction, so that is the change here. This will be lambda 2, 0.37 centimeters. It is possible you could interpret it that it was 3.37 centimeters on this side. You're going to get a different answer, slightly different. I'm interpreting in this way. If you were confused by that in the exam, you'd want to go up and ask him what he meant by that. But that's what I've interpreted, that it's 1.88 out to here, and then it's out to here. Okay, and he says the 2 colors differ by 100 nanometers. So that is that lambda 2 should be a longer wavelength. So lambda 2 minus lambda 1. The one that's further out is actually got a longer wavelength. The shorter wavelengths undergo this interference process more quickly as we start to move off. So this is actually the nearby one is a shorter, higher frequency, shorter wavelength than this one. And he says the 2 differ by 100 nanometers. And so we've got that relationship. We also have the idea that they are at, I would write this twice, so that D, I don't know what D is, by the way, in the problem, or does he tell us? Not in this one, he doesn't. that d times the sine, and in this case I think 1.88 centimeters and 1.5, we could say, yeah, I think that's reasonably a small number. Usually anything less than 20 degrees is pretty good. So then d times the sine, which is going to be y1, 1.88 centimeters. All over the length, 1.5 meters, so that's d sine theta is equal to m. Now, are these in the first order? He does say in the first order, so that's m equal to 1 times the wavelength. That's going to be lambda 1. And then we also have d times y2, which is going to be 1.88 plus 0.37 centimeters all over 1.5 meters is equal to 1 times lambda 2. Now what I can do is just take and divide these two equations. So I could, dividing these two, imagine that, the d's can cancel. Also the 1.5s can cancel. So I could end up with 1.88 centimeters, and maybe we should write this as times 10 to the minus 2 meters, so that we're not going to mess up, and divided by 1.88 times 10 to the minus 2 meters plus, well, how about just what, the total is 2.75? Well, let me see. 1.88 plus 0.37, and this is centimeters, and that's going to be times 10 to the minus 2. The 10 times 10 to the minus 2 actually drops out, and so we can do that. I probably should have lambda 1 over lambda 2. So we have a ratio here, and 1.88 divided by 1.88 plus 0.37 is got to be equal to the ratio of lambda 1 to lambda 2. So I've got that. Now the thing is, well, of course, we don't know lambda 1, we don't know lambda 2. But we do know this difference is 100 nanometers. So anyway, I think it's an algebra problem now. Between this and this, we should be able to solve for both lambda 1 and lambda 2. So okay, so this is this idea. Okay, there's a similar one, number 8. I think I'll just let this one go. Work on it if you get stuck. I think you've got my solutions. The same basic thing. Number 8, he has two different colors. You can see he kind of likes this theme. Lambda 1 and lambda 2. It's a little different setup, but the two colors are 2.5 centimeters apart on the screen. So I guess it's kind of very similar. What is the spacing between the two slits? So in this one, you actually you end up solving for D. Anyway, look at my solution. Now there's another interesting one here, this number 9, which is kind of weird. He's got two slits and then he puts a lens in front of it. So he likes to do this kind of thing. Number 9, it's got these two slits, and of course they would be doing their interfering. And from that, in front of that, he's going to place a lens here at 20 centimeters away from these. And he gives two narrow slits. He gives you, I'm just going to do this in terms of D. He gives you that distance D between these two. And maybe we'll write it down. 0.04 millimeters is D. we've got this lens. Now, here's where he makes use of that lens maker's equation. He has a double convex lens made of glass, n equal to 1.6. He gives you with each radii of curvature 50 centimeters and 20 centimeters. We're going to play with that lens maker's equation. We spent a lot of time on that. I don't check my numbers on that, but he does have a double concave, so keep in mind that when you're doing it in terms of the sign convention, there's an R1 and an R2. R1 is going to go in as a positive value because it's on the back side. R2 goes in as a negative value, it's on the front side. And you'll solve for the focal length of the lens. So again, that's based on the old stuff, and so really it comes down to what is that focal length. The new part that's kind of interesting here, and in fact, if I just pull out the focal length of the lens, I got a focal length of, actually I didn't, okay, you check my work, it's buried in there. What we want to do is we want to deal with the slits as an object. Now, if you have a lens here and you put a lens here 20 centimeters away, this becomes the object, and we're going to have a 1 over P plus 1 over Q is equal to this 1 over F. And again, we'll get that from the lens maker's equation, so we've got to piece that together. We want to find where the image of that is. Now, the object is going to be coming from, it's on the front side of the lens. The light's coming from the slits this direction. It's going to be 1 over 20 centimeters plus 1 over Q is equal to the 1 over F. And that 1 over F was, let me just put in the results of this. This is going to be the index of refraction, 1.6 minus 1, all over 1 over R1, which was each radii is 50 centimeters. Okay, so that's is going to be a 1 over 50 centimeters minus a 1 over a minus 50 centimeters. And so from this, of course, we get our 1 over F. We just can then solve for Q, find where the image is. And let me just kind of take a look at where did we find that. Okay, I've got a Q of a negative 38.4, and that's measured from the lens. So the image of the lens is back here. Okay, so there's this 2 slits that are back here, and that's going to be a distance of negative, so it's back behind the lens. It's a virtual image. So what's really happening, this thing is acting like a magnifying glass as I'm looking at this. These slits are back here. Now what we want to do is, this Q is this 38.446 or 5 centimeters back behind the screen. Now, the screen is, of course, way out here already, and we're going to form an interference pattern out there. That's another 100 centimeters away. And there's going to be a change. Now, the position of this thing is now has the slits back here. So there's going to be a change in the pattern out here. You can imagine if I'm looking through the lens itself back this way, I'm going to see these lenses. This is like a magnifying glass. It's going to become enlarged. It's back here a greater distance. Now, we can also get what we would call, I'm going to call it, let's say, D prime, the distance between these two. And that would be related to the magnification. The magnification should be equal to minus Q over P, and the magnification should also be equal to the image height, D prime, to the object height, which was D. So I can put in that minus Q, which was a negative 38.5 centimeters, divided by P, which was originally 20 centimeters, is equal to D prime all over the distance between them, which was originally 0.04 millimeters. So we can get a new D distance between the slits. Let me just leave it as a question mark. You can look at my papers. Now then, the idea that out on the screen, if we wanted to form an image, he's going to have a wavelength of 632 nanometers, so he's got a well-defined wavelength. He's going to want to see what happens to the shifting of that pattern when we stick that lens there. Now, the fact that the lens is there and I can look through this thing, the light emerging from this lens is coming, it appears as though it's coming from this slit that's back here. The screen is going to effectively see the same thing. So when I'm out on the screen, there's going to be some, let's say, maximum out here that we're going to be looking at. It's related, maybe some position Y. I'm going to assume small angles. There's some L away. Oh, actually, let's see, be careful. I don't want to do it from the center of the lens. Keep in mind that the slit, maybe I'll change colors here just to emphasize this, that I'm getting the light effectively coming from here as though it's coming from the lens. Actually, this light is coming this way, goes through the lens. These are, these are virtual rays. And coming out, and this one ends up coming here. This other slit is going to, again, be virtual rays. Once it comes out of here, it's going to, effectively is coming back to that point up here. Anyway, this is up at the maximum. So we can make use of that D times the sine of theta, which is going to be approximately Y over L, is going to be, actually I want to use D prime since it's coming from back here, is going to be equal to M lambda. And was this the first order? Yeah, first interference maximum. So this is M equal to 1. So then he can find where that Y is, where it's going to strike on the screen. But hopefully you can see this is kind of divided into two problems. One, he does make use of the lens maker's equation and ties that in with the image formation. And the idea that the slits can be the object, and they can, when we put the lens in there, we can get them at a different position. That's going to change L. In fact, L here, just to make this clear, L is going to be this, not only this 100 centimeters, but it's going to be plus this whole distance back to the slits, or image of the slits. This is going to be absolute value, so that's going to be plus 38.5 centimeters. And so the distance to the screen is 138.5 centimeters, and that would be L. So all that's going to change. Also, D is going to change because of the magnification, and so that's going to alter your pattern. Okay, wow, there's a lot of stuff. Okay, another type of interference that we deal with is thin film interference. Similar idea in some respects. Thin film. If I have something, let's say like a soap bubble, and I've got, let's say I'll do something like this, and let's say this is soap. And it's got an index of refraction of, let's say, 1.5 in here. And let's say we've got air on either side of the soap bubble, so we've got n equal to 1, n equal to 2. If we shine some light in on it, we're going to get a reflection and transmission between these surfaces. If I shine the light in, now all of the stuff we're going to be dealing with is really being shot orthogonal to the surface. It's coming straight in. For clarity, we're going to kind of draw it at an angle so that it's coming in. It would undergo some refraction. We're not, again, we're coming in straight, so I'm not so worried about that. So I'm just going to go ahead and draw this. Maybe it's refracted a little bit. And then it's going to come out and emerge out the other side. This is all going to be transmitted light. It goes through this thin soap bubble and does this. Now there's also some things that can happen, that there's going to be some reflection off. And this reflected light, as it goes from a low index to a high index, this idea when it hits this surface, there's going to be a change in phase. I'm going to put a little circle around that change in phase. So it gets flipped over, and it's transmitted always in phase, and always transmitted in phase here. But there'll be another little reflection happening here, where we have a change in wait a minute, I made that 2. This is back to the air, which is 1. There's going to be a reflected light coming back and is going to emerge. From this one, this reflection, though, is going from a higher index to a lower index, and there's no phase change on reflection. There's no change on transmission. So the idea that if we have some thickness of this film and we want to talk about what's going on here, we say that right away from just this point where there's a change, where there is one change of phase, that it should be a minima, and that should be when the idea that there's a phase change for this one, but not this one. So the two of them are automatically out of phase. That's going to be a minima. There will be this the light that travels through the medium, through that medium, through a thickness t, that is there and back 2t. If that's equal to a whole number of waves, that's waves inside the soap bubble, that whole number of waves would put these two back into phase. So now one thing we want to do is that the wavelength in the medium, very often we want to express that in the wavelength of free space divided by the index of refraction of the medium. And so usually we'll write this, and we'll just go ahead and write this as 2nt, just first off, is equal to m times the wavelength, but that wavelength is in free space. We're accounting for that it's in the medium or the soap with this n. So the idea is I've got a whole number of waves that are in this space. There's already destructive interference, so it's going to be a minima. So then I can write that for a minima, this 2nt is equal to a whole number of waves in free space. Now we can get a bright fringe, or a maxima, or maybe I'll just call it bright. In fact, maybe I should have called this minima. I like to be a little more descriptive of dark, in that there's going to be destructive interference, going to tend to wipe out the light. If in this path difference, 2nt, I have a whole number of waves, a whole number plus another half of waves, I'm going to have a bright fringe. And okay, this is for what we call reflected light. So this is reflected. There is also some light that is transmitted. That's on this side. So for transmitted light, we have the light. What happens is there's going to be another reflection where I'm going to have this transmitted light is going through. This reflected light will also not only transmit through, it will have a reflection, and that will go through. There's also some other reflections that take place here, but principally I'm interested in these two rays. In these two rays, I had no phase change as it's going through. On reflection, since I'm going from a high index to a low index, there's no phase change here. So both of these are going through, and there's no phase change between these two. So the transmitted one is going to be, they are in phase, so this is going to be bright. And that will happen if in this distance 2nt is equal to a whole number of waves. It will be dark if we kick an additional half a wave in there in this path difference of 2nt. That 2nt is going to be equal to m plus 1/2 of a wavelength. So you notice that what happened with reflected light as compared to what's transmitted, this gave me a dark reflection. It ended up being a bright transmission. So basically any light that was blocked going this way ends up going that way. Where this was bright on reflection, where we got a strong reflected light, the transmitted one would end up being dark. So that sort of makes a bit of common sense, I hope. So make a distinction between reflected light coming back this way, bouncing off, and the light originally was coming this way and is going to transmit on through. Now, be careful about just memorizing these formulas. This was, you want to pay attention to how many phase changes you have. If we went from, let's say, air to soap to something that's even a larger index of refraction, actually, let's say soap was really real close to that of water, so this would have been a 1.33. And let's say we're going to glass, 1.5. Then there would be a phase change here, and then there would also be a phase change here. Now these rays coming out here will have undergone this one a phase change, that one a phase change. The two phase changes would cancel. And then in that case, we would end up with this being bright. And if we had an extra half a wave in here, this would be dark. So the two cases switch between them, and it all depends on the number of phase changes you have. If you have an even number of phase changes or no phase changes at all, then this is your case for bright, and this is the case for dark, and these are the opposite. The big thing is you want to look for is the number of phase changes between these rays. Okay, now this process gets played out in different ways. You've got a problem here, this number 2 pieces of glass separated by a small wire. And let me draw that picture. Okay, now we've got some microphone. Okay, now he means this slit to be very narrow in here. People get confused that with ordinary light coming in, there can be reflection taking place at all of these surfaces. All of this is going on, some transmitted, some reflected. There's all kinds of complications. Now, consider that if these distances, the width, the thickness of the glass is extreme, where these effects are only going to really show themselves when these distances are really small. This light coming through is really just focused here at this interface between the thin film. The thing is, with thick films, there is something called the coherence length of the light, which, although we could get this to happen with laser light, with ordinary white light, we're just down here at this real thin cross section. So the idea that the light's going to come through, let me angle it a little bit. Again, it's coming virtually straight on through, but it's coming down here. It's going to reflect off of that. It's going to transmit and reflect off of that. And it would also transmit. They want... okay, sodium, well, this is sodium light, looks like red, which is more yellow, coming in here. And he says there's 33 dark fringes. Well, first of all, let's get the case for a dark fringe. The idea that this first reflection would take place, there would be no phase change. Then it cuts through the air, and there would be a phase change on this one. So that would immediately put them out of phase with one another. And that the idea of a dark fringe would be if there's a whole number of waves in this space between these two. And in that case, that's going to be just 2 n, and n is 1. Well, let me put 2nt is equal to a whole number of waves. A whole number of waves is where m can take on the value 0, 1, 2, 3, and so on. Take on all those values. The index of refraction here is just 1. So n equal to 1, because we are talking about this airspace in here. And the number of dark fringes, he says, okay, there's 33 dark fringes. Now, the idea that there's going to be this pattern that is going to repeat as we go across this thin film. We're going to start off with m equal to 0. That's going to be interference down here right at the point of contact. And maybe it is a dark spot, so let me just indicate it by black. Then we're going to get another one when m is equal to 1. That's just when there's this distance 2t is going to be equal to a wavelength. And then there's going to be another one and another one. This is another one happening here. And there'll be some more of these as we go across this thing. Out here with the thickness of the wire, we should find that we're going to say that this is, let me say it's 2 times, again, n is 1. The thickness of the wire is, let me call that, let's call that capital, well, T. Let's call this capital T for thickness of the wire, and because that's what we're going to be finding. The M corresponds to, oh, there's 33 dark fringes. Now, if we're going to count these things, we're going to start at 0 will be the very first one. Then it's going to be 1, 2, 3, 4, 5, and we're going to count them all the way up to 33. So there's going to be 31, 32, 33. Now, if I want to do 33 fringes, you got to watch how you count. This first one is 0, so 33 fringes would go out to 32. So, so this is m equal to 32 is formally what you want to use. And so you'll use a 32 would be for that. And then you get your wavelength, 589 nanometers, 10 to the minus 9th meters. And then I can solve for that thickness T. And you can see what I got. I'm not sure. Okay, I got a thickness of 9.42 nanometers. Okay, so these are, again, very, very tiny little distances and tiny wavelengths in there. Okay, now he says, okay, how does it change if we put a fluid in here? Now, if we put a fluid in here, he notices that we count 46 dark fringes. So this is with the fluid. We would play the same thing. Now we know what T is now, so we would say that 2NT, in this case 2N capital T, is equal to a whole number of waves. Again, the M would correspond to 46 dark fringes, so we're going to deal with 45. Count again -1, so that's 45 dark fringes, times the wavelength in free space, that's the sodium. So we know what that is, we know what T is, then we can solve for the index of refraction. So we're just kind of playing the game twice. Now, there's something here. He says, at the edge of the plate where the two meet, is it dark or is it a bright fringe? And it will turn out to be a dark fringe. That idea of the point of contact is sometimes confused. And let me show you. Maybe do the kind of setup first so you know what you're looking at. If this was a homework problem that you had, okay, that for what's called Newton's rings, we place a lens. Usually this is done with a real almost flat lens, where we get, rather than the wedge, we get an interference pattern in here. And with the lens with circular symmetry, that picture is, I just had it back here. You'll notice where the lens actually touches the surface. That is a dark fringe. And so we're going to get the same thing. That's where this is dark, and that's again why we needed to count that as the first one. So if we get 32 fringes, or 33 fringes, we're going to, that means M is equal to 32. Anyway, that's that idea.
So for that one, we just assume that the fluid index of refraction is lower than the gas.
Ah, okay, good point. Yeah, for right now, I first did it with air. What happens, and it would be kind of the same setup if this index of refraction was less than the glass. What if the index of refraction of the fluid is greater than air, and let's say greater than glass? Then the idea is if we fill that up with this fluid, then in that case what we would have is we'd have a phase change on the reflection of this first one, but it would be transmitted in phase and there would be no phase change on the second one. So we would have one phase change. It just changed from which one was phase changed, this bottom one or the top one. And the fact that there's still one phase change, the two are still out of phase. So the pattern wouldn't change at all if that fluid was put in there, other than the spacing of that. But as far as we still use the same basic formula for that, we don't switch to the m plus a half. Okay. Yeah, there's a kind of a short answer one here. Short answer, number 1A, monochromatic light illuminates a thin piece of glass, resulting in an interference pattern. How does the interference pattern change if the thin piece of glass is submerged under a fluid that has a higher index of refraction. Same basic thing happening. It's not an airspace, but the idea that if you've got a piece of glass, and ordinarily if there was air in there, there would be some light reflected, refracted. Coming through, reflected, refracted. There would be one phase change here. There would be no phase change here. If we put this inside a fluid that had a greater index of refraction than the glass, then there would be no phase change here and there would be one here. So either way, there's one phase change, either this one or that one, and overall there's no change in the pattern because of that.
How do we know that we're using reflected light rather than transmitted?
Oh, that should be in the problem. He should make that clear whether you're dealing with reflected or transmitted. Notice that on this one we're doing with the wedge, he says, when illuminated, experiment. He yeah, he hasn't really specified reflected light. I'm dealing with that. Good point.
Same number of phase changes maybe in both cases?
We would, yeah, we would still be dealing. Well, okay, if it was transmitted light, there would be no phase change. So it would do this kind of thing. And the idea that it's transmitted in phase and it's reflected in phase. So these two, as far as transmitted light, this is the reflected light, this is the transmitted light. These two would not have destructive interference. Now the only thing for transmitted light, the dark fringes for this case, we'd put in an m plus a half. And so that would affect our number a little bit, but that would be for transmitted light. Now, he has made use of these things where sometimes he deals with the reflected light, some of the transmitted light. You want to watch the language very carefully when he's writing it, that you're dealing with, which you're dealing with, the transmitted or the reflected. And that's one reason I wanted to take you through a bit of that here. Let's get rid of this. When we've got something here, whether it's a bright or a dark, depends on whether we're dealing with either reflected light or whether we're transmitted light. The distinction between the two. And you do want to be careful with how it's asked.
You're saying transmitted is zero phase change, it's canceling out?
In this case, it's zero phase change, yeah. The idea when it's always transmitted in phase. So this light coming in will be transmitted in phase. And then, okay, now originally, let's go back to the air in here. There is this reflected light that is reflected. It's going from a high to a low index where there's air in here. That's going to go off with no phase changes. It's transmitted always in phase. There would be one phase shift on this second one coming out. And so now these two, there's one phase shift between them. The only thing that changes if we stick a fluid in there of a higher index, the only thing, this would not have a phase change, and then this one would. But there is a distinct difference between the transmitted light and the reflected light. These reverse order as far as what happens with them. Okay. Okay, wow, there's a lot of stuff in here, isn't there? Okay, so anyway, thin film. Let's talk a little bit about diffraction. The idea of let's see, I don't know. Let me just do this here. Yeah.
Transmitted never has a phase change?
What's that?
Transmitted never has a phase change?
If it transmits all the way through, it's never a phase change. Now you want to be careful that here it goes all the way through. There's no phase change. This particular ray would, if it's for glass, there would be a phase change here, and then there would be one in this path. So this is being transmitted. This one has no phase change. This one had one here, and it's reflected, and it's it would have another phase change there. In this particular case with air, these two phase changes would cancel and put them back into phase. All I'm saying is, as far as the transmitted part, it's always in phase. This transmitted ray was also reflected here and reflected off of there. There could be a phase change in that, and so that could ultimately come into play. But if it's not reflected and it's strictly transmitted, it's always done and comes in phase. Okay. Another idea, the idea of a diffraction slit. Let's kind of look at the picture of that. Would be something more like this. Yeah. Okay, we're going to shine light on a slit. It's going to spread out, and we're going to get some of these minima, and the positions of these minima are going to be in such a way that okay, across that slit, the idea that we're going to bring in some waves, and as they come in here, if we look at, think of that each of these little point sources is going to be giving off waves, and they've got just some of them illustrated here. Here we've got the very top one, and we've got the very middle one. We're going to take that slit and we're going to divide it in two, A divided by 2. And if we compare these two out on the screen, this is going to be the path difference. Now, if we get a half a wave in here, that is going to give us a half a wave will give us destructive interference between these two sources. If we have, and so in that case, let me just indicate that that's going to be this. We're going to have this slit width. Again, we're looking out on the screen at some angle theta. We've got this angle theta, and there's going to be A is given as the width of the screen, and the idea that A over 2 times the sine of theta is equal to 1/2 of a wave. That would be the first minima. That's going to cancel. So the idea that there is a point out there that these two are going to cancel. Then if those two cancel, I can look at this one and the one down here. Each pair of these things is going to cancel. This next one, these two are going to cancel. This one is going to cancel. And what we need to do is just go point by point through this thing, and everything leads to cancellation. And so that the minima out there is going to follow this relationship. And in general, we can expand this argument by dividing this thing into 4 pieces and going out to a larger angle, where that little path difference is equal to number of half waves. And in general, we can write that A times the sine of theta is equal to m lambda, some whole number of half waves. The 2's drop out. This is the general condition for finding minima, not maxima, but minima. Now, it's important to realize that m can take on the value. Usually it's 0, 1, 2, 3, and so on the numbers. For diffraction, we don't have a 0. That's not included. Because if we had a 0, that would represent the position of the maxima, I mean the central maximum. If this was equal to 0, that would only happen at theta be 0. And if theta is 0, that is back where we're at the central maximum. So theta can't be 0, m can't be 0 for this. This is just the position of the minima, and they are found with this m value. Okay, now let's tie that together with double slit interference. Okay, now the reality of a double slit is that you've got the slits have some distance between them. So let me exaggerate these slits a bit. Got an opening. And so you want to think about the centers of these slits as being separated by some distance d. And so for interference, we know that d sine theta is equal to m lambda is a maxima. For diffraction, that is the actual slit width. So that's going to be the distance between here, and that's going to be A. I'm going to assume that they're both slits are the same A. Simplify that. And this is going to be for a minima that A, the slit width. So these look very, very similar. Sine theta is equal to m lambda is equal to a minima. But again, it can't be 0. It has to be 1, 2, 3, and so on. For interference, you can have an m equal to 0. That's your central maximum. Okay, now both of these things are going on. If I've got a double slit with slits here, the idea that the projection out on the screen, suppose I covered up one of these. I would just have a single slit, and it would give me a pattern that would look like that. You've seen them as Dr. Young projects them on the screen over there. You can see that they're, fairly good size. Compared to the size of these slits and the distance between them is really tiny. We're going to get a pattern looking like this if I covered up one of the slits. If I covered up the other slit, I'm going to get a pattern that looks like this, only it's going to be shifted by less than a hair over this way. And the right one is shifted that way by a hair. This one is shifted that way by a hair. And you would think, according to your kind of common sense, that the light coming from the two slits, when they hit, is going to give you that kind of pattern. Of course, we know that what really happens is that it interferes. So this is what we see out on the screen. This is a combination of the interference as well as the diffraction. Notice that the interference fringes, we got dark in here. And we still have these bright fringes. This is very different than when we first started talking of this. We were talking about there's bright fringes all the way across here, and all of a sudden now we've got these dark things. Now what's happening here is normally, look at where your interference maxima are. That's this kind of orange line. So we've got our central maximum. This is m equal to 1, m equal to 2, m equal to 3, m equal to 4, m equal to 5. And there would have been one here, m equal to 6, only it's not there. So normally I'd have constructive interference, but the idea, if there's no light there, I'm not going to see anything there. There's just a dark band. So the idea is I've got both of these things going on. One out on a point on the screen, just some theta away off here. Let's say we go off here. This is the first diffraction minima, and it lines up with the sixth, m equal to 6, interference maxima. So these two are looking very similar. I'd say that we'd say out at some point on the screen, d sine theta is equal to, let me call this m of interference, okay, for the interference times lambda. And we've got for diffraction, that's going to be a sine theta is equal to m of the diffraction, I'll call it m sub d, times the wavelength. Okay, and the point on the screen is out at the same y value or same theta value. So if we're talking about this intersection, so the idea that I have d and the sine of theta is equal to the interference fringe that is missing here was m equal to 6. So that value would be 6 times the wavelength. It's happening right here at the very first minima for diffraction. So that would be a sine theta is equal to 1 times the wavelength. I can take these two and form a ratio. I can say, well, d sine theta is equal to 6 lambda, and I'll divide it by a sine theta is equal to 1 lambda. And the lambdas go out. The point on the screen is the same, so the thetas go out. And so I just have d to a is equal to 6. So that tells me the distance between the slits is 6 times the slit width. So this, whatever this is, it's 1, 2, 3, 4, 5, 6 across this way. From just this picture, I can tell that. There's not much more I can tell without knowing the position on the screen, what these wavelengths are. But all of that does drop out, and we just have this kind of simple ratio to the distance to the slit width. Okay, so that's kind of an example of this. These two get kind of modulated, so they, the idea of this blue line is we sometimes say the diffraction envelope. That's going to modulate the intensity of the interference fringe. And so it's really the combination of those two. I think I'm just going to leave it at that. Keep it conceptual.
How do you count the 1 and the 6?
The 1 and the 6? Okay, I was counting. These are the interference fringes. So let's see now. This one is 0. So that's 1, 2, 3, 4, 5, and I'm missing the 6th one. Okay, and then as far as this one, this is the central maximum. This is just, well, that's the first one, so that's M1. So that is, keep in mind these are both integers, but one is the interference integer is 6, but the integer I use for diffraction for the first one is just 1. And then forming that ratio, we can get that. So this is a kind of a classic test question. And he's made use of this one in the past, trying to get all the ones that he's used and not doing so well.
So if you get like this, they give you the space in between each slit, like say a centimeter apart or something like that.
Yeah.
You do the reciprocal of that to find the distance, or the d, or whatever.
Find the d. Oh, yeah, if I had any one of these, for what I'm looking at here, I just know the ratio of A to D. So if I was given one of these, I can give you the other one. Maybe I'm missing your question.
It was just like a couple of questions on homework. Kept giving the slit spacing or grooves or whatever was like a certain amount, like 1 millimeter or something like that.
Oh no, I think you're maybe thinking there's a with like the diffraction. Yeah, there's a thing like diffraction gratings. These are you need to get the distance between the lines. And those are typically given, like these is 500 lines per millimeter, so that's really tiny. You need to get the distance, so you take 1 millimeter and divide it by 500, and that would tell you what the distance is between any two adjacent slits. So this is, maybe we can look at that one later, or if you're not clear on that. So I think that's referring to a little different question. Okay, now this idea of diffraction, this is kind of with a slit. We can take this idea and also explore it with the idea of a circular opening. And let's see, I'm looking for, I thought I had a decent picture. Well, let me put this one up here. Actually, forget this for now. If we shine light, like let's say laser light, through not a slit but a circular opening, we're going to get a very strong interference minima, diffraction minima here. There's also going to be some more of them. They actually form a set of rings. For our purposes that we're going to do, and the only thing we're going to do with this circular aperture is deal with the position of this minima. So the idea is this, that, let me kind of sketch it. If I have, let's say I've got a screen with let's say a hole cut out of it, and it's got a hole with a diameter of D, and I'm going to shine some light on this, and I'm going to call this the axis, and I can project this back on the screen. The idea, if I'm shining light on this thing, it's going to act a lot like the single slit, where it's going to spread out. So it's going to give me a large central maximum. And then as we go out further, there's going to be a minimum. Okay, so now usually we'll say that this angle here, and we'll just call it theta minima, and that's measured from the center of this thing up. The idea is, normally I'd say, well, I'm going to use d sine theta. This is for a slit. It's a sine theta for a slit. It's the A is the width of the slit times the sine of theta is equal to m lambda. And we're going to do m equal to 1, so we'd write this as A sine theta is equal to 1 times lambda. And for small angles, we could say theta is approximately equal to 1 lambda all over A. And we're going to do something similar to this, and we really need to be able to integrate over this circular aperture. But the idea that similar to this for this, instead of a 1, when you do the mathematical integration over the circular aperture, you get a little bit of a different change. You get theta is approximately equal to 1.22 lambda, and then instead of the size of the opening, the size of the slit, we have an opening here, which is the diameter of this opening. And so that's what that D is. And so that's the diameter of this opening. And we have this 1.22. You're just going to make use of this whenever you're dealing with a circular aperture. And this represents the minimum for the description of where this minima occurs. Now, we'll make use of this when we deal with problems that deal with what we say resolution. And here's where we'll take this idea. Let's say we want to resolve something, that is, with a telescope or something, and how well can we resolve things? The idea for a resolution is this, that, well, let me do this first. Okay, so let's say I've got this opening with a hole cut out of it. It's kind of idealized. It could represent the diameter of a telescope lens, anything where the light is going to penetrate through that. As it goes through this circular aperture, it's finite and is going to start to diffract. It's going to start to spread out. Now, if we have some distant sources of light, and I can't get too far away, but imagine we've got like a distant star that is going to be emitting its light. It's going to be traveling. It's going to go through this opening, and it's going to diffract. When we get over to the screen, it's going to form its image here, but it's going to be kind of a blurry image because of this diffraction. And it's going to have its minimum around it, and it's got some kind of a width, and that's the best we can do for this distant star. It's going to be kind of a blurry image. Rather than red, it would appear whitish, but it's going to look something more like that. Now, if we have a second thing that we're looking at, let's say a second star, let's say it's over here. The light from that star is going to come through the slit and is going to present its image over here. And we're going to get that kind of separation of these two. And there'll be some angular spread between the two, that theta, and that would match with this theta. Now, the idea here, we would say, well, I can clearly distinguish there's two stars, a photographic plate. I've got two, maybe they're a little blurry, but I've got two images of stars here. And I want to zoom in, and I want to see if I can see anything any closer. Now, the idea of we've got two of these things, we've got two of these patterns, and here I would say I can clearly resolve it. As these things get to be closer together, they start to mush a little bit, and it gets a little more confusing. I'd look at this and say, yeah, we've got two sources. They're not quite as spread apart as mine are. As they get to be closer and closer, they start to blur a little bit. And now at this point, this is what we're going to say is the limit, or Raleigh's criterion for the limit of this interference, where these two are almost on top of one another. But I could say, well, I can still make out, well, there must be two of them there. That might be stretching a little bit. There's no one place where this really cuts off. However, if they do get too close together, then they really do overlap, and you look at that and say, wow, that looks like it could be just one source, not two. Maybe it's brighter because there's two of them, but I can't really see any spatial difference between the two. So the idea of being able to resolve something through a circular aperture, we want to use Raleigh's criterion. And here's the basic idea, is we're going to get them close enough together, and this is kind of an arbitrary choice, but they chose that the maximum of one sits right at the minimum of the other one, and this one's maximum sits at this one's minimum. Meaning that the angular spread of those two things, if I want to bring them closer together, I want to get them so that they start to more kind of overlap. And the maximum of one, I want to sit at the minimum of the other. It's kind of hard to draw, but anyway, the picture is probably more telling. The idea that when we get these things closer, we're going to be right at the minimum angle. And the idea is if the maximum of one is at the minimum of the other, the idea that theta minimum is equal to a 1.22 times the wavelength over the diameter of the opening. So again, this is the diameter of that opening, or the lens, or whatever we're letting that light through. Now the thing is, they want to keep clear is that, you know, maybe this is really tiny, and this could be astronomical distances. There could be some distance between these stars, let's call that y, and they could be some big distance L. In this case, we just say, oh, well, the tangent of theta, this angle between these two, is going to be y over L. Now, we're going to be dealing with small angles, so that theta is approximately equal to y over L. And we also have this idea that whatever angle that is, we want it to, if we're going to just resolve it, to be equal to the minimum here. So we'll bring these two ideas together, that y over L is just equal to 1.22 times the wavelength over d. And so if you could get the distance, let's say y, the separation of these two stars, where you would be able to actually see it maybe through your telescope down here on Earth. This is the basic idea. This can be applied a number of different ways. On the practice problems, you can look at number 5. It's been said that a top-of-the-line spy satellite can read the letters on a pack of cigarettes. Okay, he's a distance 250 kilometers above the surface. So this is just really L is 250 kilometers. He wants not these to be stars, but this would be the letters on a pack of cigarettes, which, assuming the letters are 3 centimeters high, so this is just equal to 3 centimeters. We can do this ratio. This, of course, is a real small, narrow angle, but we can go ahead and do that. We do need to know the wavelength of light, and he doesn't give it here. I believe in my solution, I said, well, you're probably using white light, and I used just the middle of the visible spectrum, between 400 and 700. I just said, well, let's choose 550. You can resolve things with a little shorter wavelength. You should be able to get a little better results. So violet light might work better than yellow or red light, but it's probably not a lot better, and it might be weaker. So again, all this stuff with resolution, it's just kind of a fuzzy dividing line between what you can see and what you can't see. So once you get this basic idea for doing this, these are actually quite trivial problems. But if you haven't seen it, it looks really scary. Okay, so let's see. Is there any... Boy, we got a lot to cover, and I feel like I've left out things we should be talking about. But oh, let's see. One other topic that we should probably hit before we depart is polarization. First off, let's do a little recap of the idea of a polar filter. And I think Dr. Young did this. I think it was maybe just your last session, and hopefully it's fairly fresh. The idea that we have these polar filters, the first polar filter, I'm going to make an argument in a minute, will be half the intensity. If I put in a second polar filter in the same direction, it looks a little dimmer. An ideal polar filter, it would look the same. And if I cross it at 90 degrees, then it cuts out the light. So I've got a bit of light going through one of these things. It goes through one or the other. If I cross the two, nothing gets through, so it doesn't get through two sheets. But if I take a third one and stick it between them, that can get through. So let me come through this other angle here. Okay, it's a little. So it doesn't get through two sheets, but it does get through three sheets. So how does that work? Okay, here's how I like to think of polarized light. Light is an electromagnetic wave. It's a transverse wave. And as it's approaching you, let's say the light is coming at you, it can vibrate in a vertical direction, a horizontal, or anything in between. And so let me just indicate that vibration, and this is unpolarized light, would be a mix of all of these possible polarizations. So this is unpolarized light. It's scattered in all directions. And again, the light is coming at you like this. Now this is equivalent, if you think about all of these vectors, they're electric field vectors doing this, and I could break them up into X and Y components. So I can take this and I can say that I'll just decide that I want to have a particular axis. Let's say I want my x-axis like this, my y-axis like this, and I can break these up into components, both x and y. I can add all the components, and I should be able to resolve this thing into E in the x and an equal amount if it's unpolarized and the same in all directions is E in the y. Got these two. And we've got this. Now if I take this and I put a polar filter over it, take one of these sheets and lay over it like this, and it has a particular direction, kind of what we call an optical axis of this thing, and maybe I'll put that in blue, and let's say it's vertical. Now that indicates that anything going in that direction is going to be let through. It would block it in the x direction. So I'm going to be left with just the vertical component. Now if you think about it, the original intensity of light, call that I naught, when it's going through the first filter, that first filter would let half of the light through. And so the intensity of this first filter, we'll just say, is equal to 1/2 the intensity of the first bit of light. This is true for unpolarized light to now polarized light. And this will absorb everything else in the x direction. Now once I have this, I can put another filter on here. Let's say I put the filter on at an angle like this and have a polar axis that looks like that. There's going to be an angle between that axis and E. We'll just say there's going to be an angle theta there. And what we do with this is that electric field is going to have components along this. And so what's going to get out is the, maybe I'll draw the result over here. And now we're going to break this up into components, one this way, one this way. And let's say this first one coming out of here is E in the y, or let me just call that E1. That's the electric field from this first filter. And there's going to be an electric field coming out of the second filter, and that electric field is going to be equal to E1, and it's going to be just the component here. So we're going to use the cosine of that angle theta, and that's going to be the relationship for the electric field coming through that filter. In terms of the intensity is proportional to the square of the electric field, square of the amplitude. So the idea that E2, the intensity from the second one, is going to be proportional to the square of this, which is going to be proportional to the square of that, which will be the intensity 1 times the cosine squared of the angle between them. So this is one you want to get used to. And the light is coming through here polarized. It is now changed direction. It is going this direction. So if I think in terms of the next step, it was E2 was going this direction. And now if I put a polar filter and line it up like this, where along my central axis or my principal axis, let's say I lay this horizontally, then that E2 can become coming through this filter as in this next filter as E3, and I break that up into components, and so E2 now becomes E3. And here E3 is, we got another angle. Maybe it's, I could have called this one theta 1, call this one theta 2, and then this is going to be E2 times the cosine of theta 2. To get the intensity, I3 is going to be equal to I2 times the cosine squared of theta 2. So you can put all this together. You can say that I3, the intensity through the third one, is going to be I2. I2 was I1 times the cosine of theta 1 squared times the cosine of theta 2 squared. And also I1, though, the very first one is automatically a 1/2. And so I3 is equal to just 1/2 I0, the original intensity of the light, times the cosine squared of theta 1 times the cosine squared of theta 2. And so that's how we would go through those filters. That's just two of them, and the light that's emerging from them. We could do this for any number of them. We just keep tacking on these extra cosine squared terms. So you could get something like this on the exam. All right. Let's see. Well, okay. I think we've kind of covered most all the topics, at least in a bit of detail. Not a lot of things we've finished with. So I'll be around tomorrow. Feel free to drop by if you have some questions and as you're studying. And good luck. Boy, there's a lot of stuff in here, isn't there? A lot of details. Oh. Yeah, you're welcome.